Hey everyone, welcome back to Pythonic Pioneer. In today's video, we'll be continuing with our revision series. This is part 3. So if you haven't watched part 2 and part 1, you can go back and watch them. This is mostly about graph traversals, should be a short one, highlighting the most important points of depth first search and breadth first search as well. So let's get started. Graph representation. When you get When you think about graphs, the first thing you should be thinking of is how to implement a graph data structure and what is the choice that you have. Do you want to use an adjacency list or an adjacency matrix? In interviews, generically we use adjacency lists because they are space optimized, hence they require less space. And you should also be able to implement functions to add vertices and edges to the graph. So in your interview, this is what you should be doing initially. So there should be a class graph, def, init function, which is basically a constructor, which takes in an argument self. Self.graph will be an empty, let's say default dict. I usually do this a collections.default dict. You can also put it as an empty list or an empty dictionary as it is here. Def add vertex. So this function will add a vertex, takes in the self and the vertex as well. So this will be called with an object. So when you have self in it, right, this function will be called with an object of this class. So you have to initialize an object first, as we have done here, g equal to graph. So g is your object, and then you can call these functions add vertex and add edge with your graph object. So only for this graph. When you select like add vertex and pass in a vertex, say A or B, if vertex is not in the graph, then it creates a new entry with an empty list for it. And when you add an edge between vertex 1 and vertex 2, in like the for the graph for this key vertex 1, that is A, it appends vertex 2 to the list, and for vertex 2 it appends vertex 1 to the list. So it will be like the graph will look like this dictionary with a key A and a list with only B in it, and a key B with a list A in it. So that's what the graph representation is. Next, we have the depth first search algorithm, which is for exploring or traversing a graph by starting at a source vertex and moving as deeply as possible along each branch before backtracking. Let's read this again. DFS is an algorithm for exploring or traversing a graph by staring at a source vertex. Oh my god. That was just a way of getting your attention to see if you're actually listening. I do that sometimes a lot. But anyways, coming back, DFS is an algorithm for exploring or traversing a graph by starting at a source vertex and moving as deeply as possible along each branch before backtracking. It proceeds by visiting a vertex, marking it as visited, and then recursively exploring adjacent and visited vertices. When there are no more unvisited neighbors, DFS backtracks to the previous vertex, continues exploring. When we use DFS to systematically explore all possible paths in a graph, making it useful for tasks such as finding connected components, searching for paths, and solving maze-like puzzles. Write DFS algorithm to traverse a graph and print the vertices in DFS order. Def DFS. This takes in a graph, the start node, and if the and like an empty array which can be like visited as none. So this is basically because this is not the outer function. We are considering this as like not as our util function, but directly the function that gives us everything. So that's why we have this visited list, or let's say set, because it will have unique elements. So if the visited is none, then it is initialized to set for the first time. If start is not in visited, that is, the start has not already been visited, print start. So print this node and add this visited node start to the visited set. And for neighbor in graph of start, DFS of graph neighbor visited. So what this does, it comes here, prints the node, so let's say the neighbor that we are starting for the next pass, adds that neighbor to the visited list, and then again goes into the neighbor of this new neighbor node. So that's what it does. So it keeps going on deeper and deeper. Once it can't, go back anymore, it comes back, backtracks, and that's how it goes. This is just a revision. If you actually wanted to go into depth of how this works, like right now, the state that I am, I can visualize that in my head. If you can't, you should definitely be watching a tutorial video or read up on this. I might make content on this, but this is mostly focused on revising and like all the concepts and you're just quickly going through all of the topics. This is what that is. Coming to the time and space complexities of depth first search in a graph, it depends on various factors, including the graph structure, the representation of the graph, and the specific implementation of DFS. However, we can discuss the general complexities in terms of the worst case scenario. Time complexity. The time complexity of DFS in a graph is typically big O of V plus E, where V is the number of vertices, nodes in a graph, and E is the number of edges in a graph. In the worst case, DFS might visit all vertices and edges of the graph. Each vertex is visited once, and each edge is examined once to check if it leads to an unvisited vertex. Therefore, because we have that visited array, the overall time complexity is linear because once a node is visited, it's never visited again. So the overall time complexity is big O of V plus E. Space complexity. The space complexity of DFS depends on how the algorithm is implemented. The two common ways are the recursive DFS, which we looked just now. When implemented recursively, DFS may have a space complexity of big O of V in the worst case. This is because the function called stack stores information about the vertices being explored. In the worst case, if the graph is a linear chain, that is, the graph has no left and right nodes, it just keeps on going down and down and down. So that if the graph is a linear chain, the stack depth can be V, and then in that case, the time complexity will be big O of 2V, which comes to V basically. And then there's iterative DFS with a stack. In an iterative implementation using a stack, the space complexity is big O of V as well because it depends on the maximum depth of the stack, which can also at most be V. In practice, the space complexity of DFS is often dominated by the size of the call stack for recursive DFS or the explicit stack used for iteration. However, for graphs, many vertices and limited recursion depth or stack size, the space usage might be relatively small. The space complexity for DFS is related to the depth of the recursion or the size of the stack, which is influenced by the graph structure, which is also very, very important. In graphs with many branches or deep paths, DFS may require more space. Breadth first search. BFS is an algorithm for exploring or traversing a graph by starting a source at a source vertex and systematically exploring all its neighbors at the current depth level before moving on to the next depth. Right. BFS is an algorithm for exploring or traversing a graph by starting at a source vertex and systematically exploring all its neighbors at the current depth level before moving to the neighbors at the next depth level. It begins by visiting the source vertex, marking it as visited, and then visiting its neighbors. BFS continues by visiting the neighbors of the neighbors layer by layer until all reachable vertices have been visited. We use BFS when we want to find the shortest path from source to target in an unweighted graph, or when we need to explore the graph level by level, ensuring that closer vertices are visited before the more distant ones. Write a BFS algorithm to traverse a graph and print vertices in BFS order, and implement BFS using the Q data structure are the main 2 points that we're going to look at here. So there's a BFS function, def BFS, taking in the graph and the start node, you initialize the visited set as empty and Q will be a doubly ended queue DQ with the first element in that being start. That's the start node. So while the queue is there, it's not none. While queue, vertex will be q dot pop left, so it's popping from the left, and it'll be popping from the left, and it'll be appending from the right. So that's how the queue is working. If the vertex is not already existing in the visited, print the vertex and then add that to the visited. And now q dot extend neighbor. So for each neighbor in the graph vertices neighbors, add it to the queue if that is not in visited. So that's how this keeps going on. So as long as there's more like nodes added to the queue, it keeps running, and each level in the graph is getting printed. So breadth-first search is typically implemented iteratively using a queue data structure as shown in the code that I've provided. This is because BFS explores nodes level by level, and using a queue is a natural way to keep track of nodes at each level. While it's technically possible to implement BFS using recursion, it's not the most straightforward approach and can lead to increased space complexity and potential stack overflow issues for large graphs. BFS naturally lends itself to an iterative solution, and the provided iterative code is a standard and efficient way to implement it. So this is the generic way how you do it. So that's it for graph traversals. This was a very simple one. There's a lot more. There's also level order traversal, which is basically the same as BFS. Then there's vertical order traversal where we go in vertically. Then there's traversal from the right. So if you have a tree, let's say a big tree, or like a graph, and if you're looking at from the right, if you're looking at it from the left, all of these things, but we'll come back to it later on. We'll be covering the most important topics, and today we looked at depth first search and breadth first search, and also looked at the code. The main things to remember from this is the visited set. The visited set is very, very important, and generically the main thing is having a visited set, then checking if, so for this part, let's say if we go here, what did we do? DFS graph start. So if start is not in visited, that is the start, this node has not been visited. This is very important. Why do we have the visited array? To check that we don't visit an array, a vertex twice. So whenever we are going through a vertex, we first need to check that it has not been visited, and then we need to print, if it has not been visited, print it, add it to the visited array, and then go through all of its neighbors and only add them in if they have not been visited. So for the recursive case, this whole logic takes care of it, but in the BFS case, before we add this to the queue here, we need to check if the neighbor is not in the visited list. So that is very important. So the first thing will be having a visited set to take care that the same node is not visited twice. And so the first thing is to check if the current vertex that we are looking at is there in the visited set or not. And if it is not there, print it. Then go through all of its neighbors. Yeah, go through all of its neighbors, and then that's it. Like that's all the logic that is there. So that's about this video. Thanks for watching. If you like this video, feel free to like, share, comment, and subscribe. Have a great day.